Hello everyone. I'm here to present on behalf of Team Antonio, and our topic is B-spline basis functions. And my name is Darshan Gumadi, and these are my teammates Venita, Komali, Rohit, and Naseem. So we are going to present all these topics for today in the B-spline functions, and we are Team Antonio. So let's get into the introduction. So he's the Isaac John Schoenberg in the picture, and he is known as the father of B splines. He is a Romanian mathematician who is renowned for this work on the splines, and because he coined the term called B spline functions, he's known as the father of B splines. He invented the polynomial functions of B splines. The when it goes to the history of the B-spline functions, it has been deduced from Draftman spline. He basically used a technique to bend a straight line using a whale-shaped weights into a curve, crafting an art form. You can see from the picture there are a few weights which are shaped into a whale. He called them as tucks, and to get the designated curve or desired curve, he has used to he has used these weights to put them into a shape where he can pass a flexible plastic wire into them and to form a curve he desired. And you can see there are markings of the pencil behind, and he tried to mark those markings along the line of this plastic curve, and so that he can get the desired curve functions. And from these technique from these draftman splines, the B splines has been deduced. And our team our friends team called Amanda has explained about the polynomials and Bezier curves and their functions. And let us see what are the limitations of those techniques. And we can see there are few limitations when we get onto the work with the curves with single polynomial and rational segments. We do need a high degree in polynomials. And example to pass a polynomial Bezier curve with n data points, we need a degree of n minus 1, and a higher degree polynomial is needed for complex shaped figures. When we are working with high degree polynomials, we can see they are numerically unstable, inefficient to work, and complicated processing. Single segment curves are not good for the interactive shapes, and when we use Bezier curves in above cases with control points, but the solution isn't so local, so we can't use them all the time. And for above limitations, we got the piecewise polynomials, and that is the solution we acquired. And coming to the piecewise polynomials, the term itself says dividing them into the pieces, dividing each from the each control point of view. And talking about the solution we have produced in the piecewise polynomials, let us consider an example curve C in the figure 1, and these are produced in the piecewise polynomials from let us call this curve as a C of k, and we have three segments in the curve, which is C1 of k, C2 of k, and C3 of k. And the values below, all of the values are in the range of 0 and the 1. The parameter values below k naught is equal to 0 less than or equal to k1 less than or equal to k2 less than or equal to, and it's is equal to 1. So they are all lying between 0 and 1, strict range of 0 and 1, and are called the breakpoints in the curve. The mapped endpoints of three polynomial segments is denoted as Ci of k, where 1 is less than or equal to I less than or equal to m. The level of continuity is maintained to join the segments. And you can see the curve here, and these are the control points C1 of k, C2 of k, and C3 of k. So further taking the same curve here, we are going to do a piecewise polynomials in Bezier form. In piecewise polynomials in Bezier form, from the figure 2 in the slide represents the piecewise curve along the divided segments marked in blue. We represent this in Bezier form of equation Pi of j, where I is the control points and j is the segment. We are taking the previous curve to divide it into the segments of cubic form. The breakpoints k, k0, k1, k3, k2, k3 remains the same as we divide them into the cubic form. We get 12 control points. We also obtain a vector space V consists of all piecewise cubic polynomial curves on the curve C. At points, the old points get equal to the new divided points. We got P3 of 1 equal to P0 of 2, P3 of 2 equal to P2 of P0 of 3. So you can see them here. These are the segments formed P10, P11, P21, and P31, P02, P12, and P22, P32, and P31, P32, and P33. So these are the different segments. At segments, when we have divided them into the segments, there are few points which join with the existing control points. So these are the two cases what we have mentioned here. P3 of 1 equal to P0 of 2, and P3 of 2 equal to P0 of 3. We get the vector space V naught. This is the vector space of all piecewise cubic polynomial curves on the curve C naught and the continuous and zeroth level of continuity. This is called the zeroth level of continuity. And the vector space obtained V naught is the subset of the whole vector. And piecewise polynomials in Bezier form, we try to impose first level of continuity C dash C1, and with assumptions that k equal to k1 and p3 of 1 equal to p0 of 2. Let v equal to u minus u naught by u1 minus u naught, and w equal to u minus u1 by u2 minus u1. So these v and w are the local parameters when we consider on the intervals of u naught and u1 and u1 and comma u2. Then the u and w lies in between 0 and 1 value. The first level of continuity at u1 implies the 1 by u1 minus u naught into c1 of 1, v equal to 1, c1 of 1 into u1 equal to c2 of 1 into u1 equal to 1 by u2 minus u2 into c of 1, where w equal to 0. So the P31 and P32 can be written in the terms of P21, P12, P22, and P31. The vector space V1 and C1 continuous piecewise polynomials functions with the dimension 8 has been deducted here. And the vector space obtained with the continuity of first level of continuity is V1, which is a subset of the V naught and which is a subset of V. 3 by u1 minus u0 into p3 of 1 minus p2 of 1 equal to 3 by u2 minus u1 into p1 of 2 and p minus p0 of 2. So we get a by getting p3 of 1 as a subject here, we get u2 minus u1 into p21 plus u1 minus u0 into p12 by u2 minus u0. So this is the formula. This is the formula for. Let us consider the B splines defined. The term B spline was, as we discussed earlier, coined by John Schoenberg, and a spline function of degree n is a piecewise polynomial function of degree n minus one. The knots are the places where the dots meet, as we have seen in the picture earlier. All the possible spline functions can be built by linear combinations of B splines. Only one unique combination for each spline exists here. And when we consider the recursive definition of B splines, this is the most important part where we work with the higher degree values and bigger curves, complicated curves. So for p value greater than 0, comma n, and u is a linear combination of two p minus 1 degree basis functions. Computation of set of basis functions require specification of knot vector u and the degree p. Equation on previous slide can yield the quotient percent. We define this quotient to be 0. The half open interval ui comma ui plus 1 is called the ith knot span and is called the zeroth length since knots need not to be distinct. The computation of p degree functions generates a truncated triangular table. So this is the formula. Ni of 0 of u is equal to 1 if the u value is existing between the ui less than in between the ui and ui plus 1, and in all other cases it's going to be 0. Ni of p of u equal to u minus ui by ui plus p minus ui into ni p minus 1 of u plus ui p plus 1 minus u by ui plus p plus 1 minus ui plus 1 n I plus 1 comma p minus 1 of u. So this is the formula we are going to use, and we get a truncated triangular table here. and it's going to be n00, n10, 20, 30, 40. The degree is going to be each column has a different degree, and it keeps increasing, and we can form how much ever higher the degree value, we're going to get the truncated triangle table. Here the column 1 is of first degree, column 1 is of 0 degrees, then first degree, second degree, and the third degree, and so on. So this is one of the example for the degree 0 function. And let us consider the non-zero degree basis function u equal to 0, 0, 0, 1, 2, 3, 4, 4, 5, 5, 5. So this is the curve we are going to use further. And based in substituting in the recursive formula, we are going to get the following values here. n00 is equal to n10 equal to 0. It is going to be 0 in anywhere if the u value exists in between minus infinity to infinity. Practically, basically it is 0 everywhere for n00 and n10. And when it comes to n20, it is going to be 1 if the value is going to be in between 0 and 1, and rest all cases it's going to be 0. So for each and every n30, n40, n50, 60, 70, 80, we are going to get each and every value by substituting them in the following formula. And let us discuss the degree 1, and this is one of the example of degree 1. We're going to use the same function here, and the curve is going to be different, and this is the same value here. N01 equal to u minus 0 by 0 minus 0 into n00 plus u 0 minus u by 0 minus 0 into n1 comma 0 equal to 0, minus infinity to infinity. U exists in between minus infinity to infinity, and for all the rest of the values it is going to be as follows. Here you can follow here. This all we obtained by using the same formula, and we use the degree 0 as well. So we substitute in the degree 1 the values of the degree 0 in order to get the degree 1. The same way we are going to see the degree 2, where the degree 1 and the degree 0 values are used to substitute them, and the same function here as well. And all n I of 2 are 0 everywhere except on the specified intervals given here. And these are all the exception cases where you see non-zero values, and each value is obtained from the formula we got substituted.
Hello, Professor. This is Vinita. So today I'm gonna explain about some of the properties of B-spline, and we already know that concept of B-spline curve came to resolve some disadvantages of having Bezier curve. So in Bezier curve, we face a problem. Like when we change any of the control point respective location, the whole curve shape gets changed. But here in the case of B-spline curve, only a specific segment of the curve shape get changes. And we can also say like control points impart local control over the curve shape rather than the global control like Bezier curve. So and to calculate, and we have a recursive formula to. So we already know the Bezier basis functions are used as weights. B-spline basis functions will be used the same way. However, they are much more complex. Like there are two interesting properties that are not part of the Bezier basis functions, namely, the domain is divided by knots, and the second one, basis functions are not non-zero on the entire interval. In fact, each B-spline basis function is non-zero on a few adjacent subintervals, and as a result, B-spline basis functions are quite local. So, like, let U be a set of m plus 1 non-decreasing numbers, and the sequence goes on like U naught less than or equal to U2 less than or equal to U3, and so on. Here, the UIs are called knots, and the set U, that is nothing but a knot vector, and the half open interval UI to UI plus 1, the ith knot span. We called it as like ith knot span. Note that since some UIs may be equal, some knot spans may not exist. If a knot UI appears k times, where k greater than 1, then the UI is a multiple knot of multiplicity k. It will written as UI of k. Otherwise, if u appears only once, then it is like a simple knot. So there is this general formula to calculate the basis function uh, for the B-spline curve. This formula referred as a Cox-Debord recursion formula. This definition looks complicated, but it's not that difficult to understand. Like if the degree is 0, these basis functions are all step functions, and this is what the expression says. So that is like basis functions ni comma 0 is 1 if u is the ith knot span in the range ui and ui plus 1. For example, like if we have four knots ui, u1, u2, u3, and knot span 0, 1, 2, and the basic functions of degree 0 are like n0, 0, and that is 1 on, and that is 1 if it is in the range 0 comma 1, and 0 if it is in anywhere other than 0 comma 1. So like this is pretty easy to understand the formula. And like we divided the segments here, and in the segments we have knot points like n3 to n31 and n41. We calculated those. Like and we already know what is piecewise polynomial. Like here in the B-spline curve, we'll divide the whole curve into different segments. That is nothing but a piecewise. And B-spline curves have like so many properties, and some of them are like the sum of the B-spline basis functions for any parameter value is 1, and each basis function is positive or 0 for all parameter values. And there is one more, like each basis function has precisely one maximum value, and the maximum order of the curve is equal to the number of vertices of defining polygon. And there are some more, like the degree of B-spline polynomial is independent on the number of vertices of defining polygon. And there is this special property like B-spline allows the local control over the curve surface because each vertex affects the shape of a curve only over a range of parameter values where it is associated basis function is non-zero. And here the curve exhibits the variation diminishing property, and the curve generally follows the shape of defining polygon. I'm gonna explain some of the properties like local support, local impact, non-negativity, and partition of unity. And remaining will be explained by Komali, one of our teammate. So coming to local support, like for a single span of a B-spline curve is controlled only by k control points, and any control point affects k spans. So specifically changing a control point affects the curve in a particular range, and that is like only it will affect that particular segment, not the entire curve. So here if we are changing any control point, then only the particular segment of that control point will change, not the entire curve. That is the local support property. So there is this property called local impact, uh, which will say us that the value of B-spline at a point depends just on few control points localized nearby, and vice versa. Like if you modify a control point or coefficient of one basis function, it will affect just some local neighborhood. So on any span in the range ui to ui plus 1, at most p plus 1 degrees, basis functions are non-zero. Like for example, we can say it like n to the base I minus p comma p, and n to the base I minus p plus 1, and so on. Like these are all non-zero basis functions. That is like one property in the B-spline curve. And we have one more property called non-negativity, which is nothing but positivity. For all I comma p and u, where I p and u are control point, degree, and segment, the n of I comma p is non-negative, and this is already proved in D-Boer algorithm. Like in that, like for any parameter interval, the labels along the edges of the D-Boer algorithm are non-negative. So, like we can show this property using that D-Boer algorithm also. And the one more property of B-spline is partition of unity. So here, this property says that the sum of all non-zero degree basis functions on a span ui and ui plus 1 is 1. We already seen that the previous property is like all the basis functions are non-negative on a particular span like ui and ui plus 1. And this property, partition of unity, states that sum of all these basis functions is 1. And this property can also be derived from the D-Boer algorithm by setting pk as 1 for all k and observing that since at every stage of the algorithm we are taking affine combinations of the nodes, the value at every interior node is also equal to 1. Hence, the value at any apex must be 1. So we can derive this partition of unity property from this D-Boer algorithm.
Continuing with the properties of B-spline differentiability. The smoothness of a B-spline function represented by NIP of u as a whole is determined by its derivatives, which are present within the range of knots. At a specific knot, the smoothness of NIP of u is affected by both the degree of the polynomials and the multiplicity of the knot. Specifically, the function will have p minus k levels of continuity, where k is the multiplicity of the knot. This means that by increasing the degree, the smoothness of the function increases, but by increasing the multiplicity of the knot, smoothness of the function decreases. A B-spline function of a degree p is p times continuously differentiable, meaning it has p continuous derivatives. For example, a B-spline of degree 3 is 3 times continuously differentiable, so it has 3 continuous derivatives. This means that the function is very smooth and its slope does not change abruptly. Going with the continuity, a B-spline function is said to be C naught if it is continuous at the knots, meaning that the function has the same value at the knots. A B-spline function is said to be C1 if it is also continuous in its first derivative at the knots. A B-spline function is said to be C2 if it is also continuous in the second derivative of the knots. In general, a B-spline function of degree p is Cp minus 1 continuous, meaning that it is continuous in its first p minus 1 derivatives. So, a B-spline function of degree 3 is C2 continuous, so it continues in its first two derivatives, meaning that the slope and the rate of change of the slope is the same at the knots. Maximum value. This is the next property of the base plan functions. So NIP of u function has exactly one maximum value except when p equals 0. Let's understand the effect of multiple knots. Consider functions n0 to n1 to n2 to n5 to n6 to of this adjacent figure. For u equals to this set of values, functions are calculated on the following knot spans and are 0 outside these spans. We get n02 equals to the values 000 and 1. The same goes on with n12, n22, n52, and n62. Now, the word multiplicity is understood in two different ways: the multiplicity of a knot in knot vector, the multiplicity of a knot with respect to a specific basis function. The same is explained in this example. So, going to the next topic, which is derivative formulas. The derivative of a basis function is given as follows: n derivative of ip equals to p by ui plus p minus ui and ip minus 1 of u minus p by ui plus p plus 1 minus ui plus 1 n into I plus 1 p minus 1. We can prove this by induction on P. So in the mathematical induction, we take the base case for P equals to N p equals to 1, ni comma p minus 1 and ni plus 1 comma p minus 1 are either 0 or 1. Therefore nip is either 1 by ui plus 1 minus ui, or 1 by ui plus 2 minus ui plus 1. Going to the inductive step, now assume that the above equation is true for p minus 1, where p is greater than 1. To differentiate this basis function, we use the productive rule f for the derivation of multiplication of two functions, which is f into g to the derivative equals to f dash of g plus f into g dash. We get the below equation. Once we apply this derivation, this gives us the below value. So substituting the equation 1 in the equation, in this equation 2, for n dash of I comma p minus 1 and n dash of I plus 1 comma p minus 1, we get this below equation. From this equation, by Cox-de-Boer formula, we can substitute the values in this parenthesis by ni comma p minus 1 and ni plus 1 comma p minus 1 respectively. Therefore it can be written as this below equation. If nth kth derivative of nip of u denotes the kth derivative, then repeated differentiation gives this below formula, which is nip of k of u equals to p of this whole thing in the braces. From this we know that if n to the kth derivative of ip of u denotes the kth derivative of the b-spline function, repeated differentiation produces this below formula. These are the following conditions that must be satisfied when defining the derivations in terms of original B-splines. K should not exceed the value of P, and denominators involving knot differences can become 0, in which case the coefficients are defined as 0. We can also write the equation of kth derivative of nip of u in this formula as a summation, where we get p factorial by p minus k factorial over the summation of j equal to 0 to k a k comma j n I plus 1 I plus j comma p minus k. We have the initial value, say 0 comma 0 equals to 1, a k comma 0 equals to this value, and also the values of a k comma j and a k comma k. So if we have the basis function defined as in the figure A, by applying the derivation on this figure, we get the uh, following functions as in the figure B. That is the end of the derivative functions.
To define B-spline basis functions, we need one more parameter, the degree of these basis functions, P. The ith B-spline basis function of degree P, written as nip of u, is defined as follows. The above is usually referred to as Cox-de-Boer recursion formula. This definition looks complicated, but it is not difficult to understand. If the degree is 0, these basis functions are all step functions, and this is what the first expression says. That is, the basis function nio of u is 1 if u is the ith knot span ui of ui plus 1. For example, if you have 4 knots, u naught equal to 0, u1 equal to 1, u2 equal to 2, and u3 equal to 3, knot spans 0, 1 and 2 are 0, 1, 1, 2 and 2, 3, and the basis functions of degree 0 or n0, 0 of u equal to 1 and 0 elsewhere. This is shown below in the graph. To understand the way of computing nip of u for p greater than 0, we use the triangular computational scheme. All knot spans are listed on the left column and all degree 0 basis functions on the second. Properties of B-spline basis functions. Derivatives of B-spline with multiple knots. Let uj 0 less than or equal to j less than or equal to k be a strict increasing set of base points. The vector space V, where Rj lies between -1 to p, is formed by all the set of piecewise polynomial functions of degree p on uj which are c to the power of rj continuous at u equal to uj. Rj equal to -1 for all j if no continuity constraints are imposed. Then the dimension of V is defined as equal to k of p plus 1, where dimension of V equal to k of p plus 1 minus sigma of where j equal to 0 to k rj plus 1. Derivatives of B-spline with multiple knots. All derivatives of nip of u exist in the knot span. A knot nip of u is p minus k times continuously differentiable, where k is the multiplicity of the knot. Hence, increasing degree increases continuity and increasing knot multiplicity decreases continuity. Using the above property, B-spline basis function of p degree with knots at uj with desired continuity appropriately setting the knot multiplicities sj, where sj equal to p minus rj is obtained. Therefore, the following knot vector is used u, where m is defined as sigma j equal to 0 to k of sj whole to the minus of 1. Therefore, dimension of V is the total number of pth degree B-spline basis functions on U. By showing NIP are linearly independent, the term basis function is justified. This can be proved by induction on P, since the 0th degree functions are linearly independent, assuming P minus 1th degree functions are linearly independent for P greater than 0 and n equal to m minus p minus 1, where sigma I equal to 0 to n alpha I into ni comma p of u equal to 0 for all u. This is a derivative of degree 3 splines n dash of ip. From the above equations we get these equations, which implies 0 equal to sigma equal to 0 to n alpha I nip minus 1 by u I plus p minus ui minus sigma I equal to 0 to n alpha I into n I plus 1 p minus 1 by u I plus p plus 1 minus u of I plus 1. Knot vector. Once the degree is fixed, the knot vector completely determines the function nip of u. There are several types of knot vectors. A periodic or open or clamped knot vector is of the form where u is defined, where the first and the last knot have the multiplicity p plus 1. Below are the two properties of non-periodic knot vector. Knot vector of this form u yields the Bernstein polynomials of degrees p. Let the number of knots be m plus 1. Then there exist n plus 1 basis functions where n equal to m minus p minus 1. There's an example where knot vector is defined, and for instance n o comma p of a equal to 1 follows the fact n 0 comma 0 to n p minus 1 of 0 equal to 0. Knot vector notation, where u bar is defined as u equal to u of k, u cap is defined as u equal to uk plus du, u plus same as u expect uk is replaced by uk plus du. Ni bar is a basis function after inserting uk into u. Ni dot is basis function after inserting uk plus du into u. Having a non-rational B-spline curve of degree p, we are provided with c of u is equal to sigma I equal to 0 to n nip of u into pi, the derivative of the type where d by duk of c of u, here uk is a knot having a range of less than or equal to p, where p is less than equal to k less than or equal to n. These are the right and left derivatives. Define k minus p the limit. The right derivative of a b-spline curve of degree p, which is rational, is moreover a b-spline curve of a comparative degree with respect to left derivative. Both right and left derivatives have identical formulas, but in right derivative k ought to fulfill uk is equal to uk plus 1. In left, k ought to fulfill uk minus 1 equal to uk. These are the formulas for right and left derivatives. So keep coming to key points. The left and right derivative capacities are no different for the knots of variety 1. Distinction between the right and the left derivatives of curves is expected the way that various arrangements of capacities are non-vanishing for both right and left indexes. Various sets are evaporating for the knots having higher multiplicity, where the derivative functions are something very similar, cross over the record range. This graph where we can see the left derivative and the right derivative defined.
I'm going to present the topic of computational algorithms. So say let u is a non-vector of the form, let u is from u0 to urn, and we assume we are interested only in the basis function of degree of polynomial p. Assume u is fixed, and say I is represented with knot span index, a single basis function nj with polynomial p of function u, and the derivatives of the single basis function are represented as below. Find span is an integer function which returns the span index. This will determine the knot span index with input being n, p, u, and u, and this will return the knot span index. So here, if you could see mid value, it is the mid value from low to high, and this the mid value will be returned, which is the knot span index. And here is the representation of non-vanishing basis algorithm. And here is an example where we are writing out the second degree functions in general terms. Introducing the left of j and right of j notations, and by substituting the values, here will be the new equations which are represented as below. Say basis function this will be computing the non-vanishing basis functions with input being I, u of polynomial degree p, and output being n. This is an array, say n of j, which will be saved and will be returned. To compute all the values, this will reveal the basic ingredients. Say the inverted triangle of non-zero basis functions will be computed in non-vanishing basis algorithm. The differences of knots are also computed in non-vanishing basis algorithm. As a two-dimensional array of dimension p plus 1 and p plus 1, the basis functions will fit into the upper triangle and the knot differences will fit into the lower triangle. So this will use all the basis knot differences, and they are multiplied respectively by n, 5, 1, 5, 0, and 6, 0. This algorithm will compute the non-zero basis functions and their derivatives, including the nth derivative. Output is in the two-dimensional array, and kth derivative of the function is ni minus p plus j, comma p. And the two local arrays are ndu and a, which will store the basis functions and knot differences, and also the two most recently computed rows respectively. This algorithm will avoid division by 0 and also the use of the terms not in the array ndu. Here is the representation of derivative basis function. This will store functions and the knot differences, and it will compute the non-zero basis functions and their derivatives. The output is represented with DERS array. This section will compute the derivative. The solution to the problems will be the single basis function ni, p, and the derivatives of a single basis function resulted in triangular tables of the form as represented below. Here is an example for degree polynomial 2. This will computation of n3 5 by 2 and n4 by 2 is obtained from as below. Algorithm will compute only the non-zero entries and the value ni with polynomial u is returned in NIP. M is the high index of u with m plus 1 knots. This is the representation of one basis function. This will compute the basis function NIP, and as seen, output will be NYP. The n of the zeroth element of the n array will be represented as NIP. Here is the representation of the computation of the derivatives with polynomial p and n value 3. This algorithm will compute and store the entire triangle table with corresponding to k is equal to 0. To get the kth derivative, we need to load the column of the table which will contain the functions of degree p minus k and compute the remaining portion of the triangle. This algorithm will compute NIP. The kth derivative is returned in DER as k array. And here is the representation of the derivatives one basis function. Moving on to design examples. This is an example of simple B-spline curve with added knots in several locations to create an outline of butterfly. And this is the second example. This is an example of simple B-spline curve created to make the shape of the cup. First by creating the shape and then by rotating about a central y-axis. And here is a video of representing it. Blender. So Blender is an open source software which is used to develop 3D subjects. We can also use Blender to create 3D modeling, rendering, animations, and games. We are considering a NURBS curve, which is non-uniform rational B-spline curve. This one will have 4 control points and uniform knots. This is the design we have created using Blender.